Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 3.2 on properties of determinants and on calculating determinants using the method of row reduction. We'll walk through lots of example problems so you'll understand exactly what to do. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. We're first going to look at how elementary row operations can change the value of a determinant. We're going to look at this because the determinant of a matrix can be evaluated by reducing it to echelon form. When doing this, we need to know how elementary row operations change the value of the determinant. There are three elementary row operations that you can use to reduce a matrix to echelon form, and I've listed them here. The first one is called replacement, the second one is interchange, and the third one is scaling. Let's see how these three row operations change the value of a determinant when we start with a matrix A, perform row operations on it, and then arrive at a matrix B. If we use row replacement, the value of the determinant doesn't change. We say that the determinant of the matrix that we end up with is then just equal to the determinant of the matrix that we start with. Now let's look at row interchange. Row interchange changes the sign of the determinant. If we interchange a row when we reduce matrix A to matrix B, the determinant of matrix B is going to be -1 times the determinant of matrix A. When we use scaling and scale a row by a factor k, that changes the value of the determinant. If all elements in a row are multiplied by k, then the determinant is also multiplied by k. We write this as determinant of B is equal to k times the determinant of A. Let's now walk through three example problems to see how row operations on a matrix affect the value of its determinant. We're given a matrix A and told that the determinant of A equals 3, and then we're asked to find the following determinants. Our strategy is going to be to write the given determinant, such as this one in example 1, in terms of the determinant of A and make note of the changes that take place due to the row operations. In our first example, let's notice that there is a 2 multiplying every entry in the first row. We can pull out this factor of 2 and rewrite the matrix as A, B, C, D, E, F, and then -G, -H, -I. Let's now notice that we have a -1 multiplying the entries in the bottom row. We can pull out the negative and write this as -2, and then our determinant becomes A, B, C, D, E, F, and G, H, I. This is the determinant of matrix A, so this is going to be equal to -2 times the determinant of matrix A, which we're given as 3, and this gives us a final answer of -6. Let's now look at our second example. If we compare this example to matrix A, we notice that rows 1 and 3 have been switched. We're going to switch them back, and because switching rows causes us to have to multiply the determinant by a -1, we're going to write this as -1 times the determinant A, B, C, D, E, F, and G, H, I. This again gives us a value of -3. In our third example, we notice that it is very similar to our matrix A above, except some row operations have been done to it. I'm going to write the determinant of A right below this so that we can compare the two and we can see what row operations have been used. If we look at row 2, we can see that in the original matrix, row 2 was replaced with row 2 plus row 1. If we look at the third row, we can see that row 3 has been replaced with row 3 minus 2 times row 1. Since row replacement operations don't change the value of the determinant, the answer for this determinant is just going to be the determinant of A, which is equal to 3. We're now going to use what we just learned about how row operations change the value of a determinant to find determinants by using row reduction to echelon form. This method works because the echelon form of a matrix is an upper triangular matrix, and we know that the determinant of an upper triangular matrix is just the product of the entries along the main diagonal. To calculate the determinant of a matrix using row reduction, there are 3 steps that we can follow. The first step is that we'll use row reduction to reduce the matrix to echelon form. The second step is to mark any changes that we get due to row interchange or scaling as we go along. And then the last step is to just multiply the entries of the main diagonal of the echelon matrix to get our answer. Let's now walk through an example so that I can show you how to find the determinant by row reduction to echelon form. We're given the determinant of a 4x4 matrix, and we'll begin by noticing that in our first row, each of the entries is a factor of 2. We'll pull that factor of 2 out and then rewrite our determinant. We can now begin our row reduction. We'll circle our first pivot, and then we'll get zeros below this pivot. I've already listed the row operations that we'll use to make these entries a 0. We'll then rewrite our determinant again, and we'll go to the next pivot. We'll then get zeros below that pivot using these row operations. After writing the determinant again, we'll go to our next pivot, and we'll get a 0 below that pivot using this row operation. Our determinant is now in upper triangular form, and the value of our determinant is just going to be the product of the entries along this main diagonal. So our answer is equal to 2 times 1 times 1 times 7 times minus 2, which gives us a value of minus 28. Using the method of row reduction to calculate a determinant is really effective when you have a large determinant. In our next example, I'm going to show you how you can combine the methods of row reduction and cofactor expansion to find a determinant. Notice that this is the same determinant that we worked with in the previous example. Just like in that example, we notice that our first row has entries all with a factor of 2, so we can pull out that factor of 2 and rewrite our matrix. We'll circle our pivot and then get zeros below that pivot. When we rewrite our determinant, notice that we have a column that has all zeros except for that first entry. This is always going to happen when you use row reduction. We're now going to shift gears, and we're going to now use cofactor expansion to evaluate the determinant. We have 2, and we're going to do cofactor expansion along this first column. So we multiply our 2 by 1, and then we have our resulting 3 by 3 determinant when we cross out the row and column common to that first entry. This gives us a 1 minus 2 minus 1, 2, 3, 0, and 2, 3, minus 2. We're now going to use cofactor expansion on this 3 by 3 matrix, and I'm going to choose to do the expansion along the second row because it has a 0 in it. You could have equally done the expansion down the third column. Let's start by doing our plus minus pattern. We have plus, minus, plus, minus. So our answer is going to be 2 times minus 2 times the matrix that remains when we cross out the row and column common to 2. This gives us a minus 2, minus 1, 3, minus 2. And then we add 3. We cross out the column common to 3, and this gives us the determinant 1 minus 1, 2 minus 2. This is then equal to 2 times minus 2 times a 4 minus a negative 3 gives us a 4 plus 3 times a minus 2 minus a negative 2, which gives us a plus 2. This gives us an answer of minus 4 times 7, which is equal to minus 28. You can see that the methods used in these two examples take about the same amount of work. Depending on the entries in a matrix, one method may take more or less work than the other, or they may be about the same. The advantage of using row reduction is that you create a column that has all zeros except for one entry. We're now going to shift gears and talk about properties of determinants. The determinant of A times B is equal to the determinant of A times the determinant of B. This property is nice because you don't have to multiply the matrices and can just multiply the determinants. Our next property tells us that the determinant of A raised to a power is equal to the determinant of A raised to that power. It's a lot easier to raise a number to a power than it is to compute the power of a matrix. Our third property tells us that the determinant of K times A is equal to K to the N times the determinant of A, where A is an n by n matrix. The most common mistake I see students make with this is to just pull the K out and not raise it to the power that corresponds to the size of matrix A. The fourth property tells us that the determinant of A inverse is just equal to 1 divided by the determinant of A. Our last property tells us that the determinant of A is the same as the determinant of A transpose. I would suggest that you memorize all these properties. Before we walk through some example problems, I want to make 3 observations. The first is that the determinant of A plus B in general is not going to be equal to the determinant of A plus the determinant of B. The second observation is about a matrix with 2 proportional rows. When we have a matrix with 2 proportional rows, we can row reduce it to a matrix with a row of zeros. The determinant of a matrix with a row of zeros is just going to be equal to 0. The third observation is about a matrix that has 2 proportional columns. The matrix A that I've written here has columns 1 and 2 proportional to each other. This means that A transpose is going to have 2 rows proportional to each other, and that's going to lead to a row of zeros, just like we saw in our second observation. This means that the determinant of A transpose is equal to 0, and that implies that the determinant of A is equal to 0. Let's now walk through some examples and see how these properties are used in practice. In our example, A and B are 3 by 3 matrices. The determinant of A is equal to minus 3, and the determinant of B is equal to 2. We're asked to compute the following determinants. Our first determinant is a product, so we can separate it and write it as the determinant of A times the determinant of B. This is going to be minus 3 times 2, plugging in the values that we were given above, and that's equal to minus 6. Let's look at our second example. This also is a product, so we can separate it as the determinant of A times the determinant of A transpose, and that's equal to minus 3. The determinant of A transpose is the same as the determinant of A, so that's another minus 3, and we get a final answer of 9. In our third example, we have a constant that we can pull out. Let's notice that B is a 3 by 3 matrix. That means that when we pull the 2 out, we're going to have to raise it to the third power and then multiply that by the determinant of B. This gives us an 8 times the determinant of B, which is 2, and we get a final answer of 16. Our next example is a product and a power combined. We're going to pull it apart, and we're going to write it as determinant of A to the 4th times the determinant of B. The determinant of A to the 4th is the same as the determinant of A raised to the 4th, and then we have the determinant of B. Now we can go ahead and plug in. The determinant of A is minus 3. That gets raised to the 4th. and then the determinant of b is 2. Minus 3 to the fourth is 81. Multiplying it by 2, we get an answer of 162. Let's now look at our last example. We have a product again, so we're going to split it apart. We have the determinant of A inverse, and then we have the determinant of B squared. The determinant of A inverse is 1 divided by the determinant of A, and the determinant of B squared is the determinant of B quantity squared. This gives us 1 divided by minus 3 times 2 squared. Our final answer is then minus 4/3. The last topic that we're going to look at is how to use determinants to determine invertibility and linear independence. We'll first talk about how determinants can be used to determine invertibility. A matrix is invertible or non-singular if its determinant is not equal to 0. A matrix is not invertible or singular if its determinant equals 0. Let's now walk through an example where we'll use a determinant to find all values of k so that our matrix A is invertible. Since this example involves a lot of algebra, I've already written down the solution and we'll just walk through it. To find the determinant, we'll use the method of cofactor expansion and expand along the first row because that row has a 0 in it. We'll start by indicating each term with a plus or minus, starting with the upper left. So this is plus, minus, plus. The determinant of A is equal to k times the determinant that we get when we cross out the row and column common to k. That's this determinant. Plus 2 times the determinant that we get crossing out the column and row common to 2. And that's this determinant. Since we want to choose k so that A is invertible, we have to make sure that our determinant is not equal to 0. Computing these 2 by 2 determinants, we end up with this algebraic expression. Notice that each expression has a k minus 1 in it, so we can factor that out. We factor it out here on our first term and here on our second term. We then combine like terms, do a little bit more algebra, and we end up with this expression. This tells us that k cannot equal 1, 0, or minus 3. When k is any other value other than 1, 0, or minus 3, our matrix A is going to be invertible. Let's now learn how a determinant can be used to determine if a set of vectors is linearly independent or linearly dependent. A set of vectors is linearly independent if the determinant of a matrix with these vectors in its columns is not equal to 0. This is because when a set of vectors that is linearly independent is placed in a matrix, every column will have a pivot, and that's going to make the determinant of the matrix not equal to 0. In our example, we're going to use determinants to find out if the set of vectors is linearly independent. We'll begin by putting our vectors in a determinant. Since there are no zeros in our determinant, I'm just going to choose to do cofactor expansion across the top row. We'll write down our plus minus pattern and now compute our determinant. This is going to be equal to 3 times the determinant minus 4, 3, 4 minus 2, minus 1 times the determinant minus 2, 3, 5 minus 2, plus 2 times the determinant minus 2, minus 4, 5, and 4. This gives us 3 times 8 minus 12, minus 1 times 4 minus 15, plus 2 times minus 8 plus 20. This is minus 12 plus 11 plus 24 for an answer of 23. Our determinant is not equal to 0, so that tells us that our vectors are linearly independent. Be sure to check out the next video in this series where I'll teach you all about vector spaces and vector subspaces. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.